Okay, so in the previous lecture, we recalled some basic facts on compact operators and also some notions from duality theory for Banach spaces. And in particular, we proved the following theorem. Well, let's call it Theorem 1 for today. Suppose that X and Y are Banach spaces. And T is a bounded linear operator from X to Y. Then we have the following equivalences. First of all, T is topologically injective, even only if the dual operator, T star, is surjective. Second, T is surjective, even only if T star is topologically injective. And as a special case, we see that T is a topological isomorphism. Even only if T star is a topological isomorphism. Well, so this result was proved at the end of the previous lecture. Let's recall that probably the most non-trivial part here is to prove the right to left implication in part 2. That is, to show that if T star is topologically injective, then T is surjective. So all the other parts are much easier, but this one is quite non-trivial. And by the way, it's a nice exercise to understand, is it really necessary that X and Y are indeed Banach spaces? So in other words, a natural question is, which parts of this theorem survive for arbitrary, that is not necessarily complete normed spaces? It can happen that maybe all of them survive, or only some of them, or maybe none of them survives. Well, this is an exercise for you. Well, now actually Theorem 1 has the following metric analog. Theorem 2. Again, suppose that X and Y are Banach spaces, and T is a bounded linear operator from X to Y. Then, first of all, T is an isometry even only if the dual operator T star is a co-isometry. Which means that it takes the open unit ball until the open unit ball. Second, T is a co-isometry, even only if T star is an isometry. And as a corollary, T is an isometric isomorphism, even only if T star is an isometric isomorphism. So this theorem can be considered as a metric analog of Theorem 1. In fact, well, topologically injective operators are topological embeddings, and isometries are isometric embeddings. And similarly, surjective operators. So what are surjective operators? We know that by the open mapping theorem, surjective operator is nothing but a surjective operator between Banach spaces, is nothing but a quotient map. And is nothing but an open map up to topological isomorphism. More precisely, let's recall the following picture. If we have an operator from X to Y, we can consider the induced operator from the quotient module of the kernel to Y. And we know that this operator from X to Y is open, or equivalently surjective, if and only if this induced operator is a topological isomorphism. So in other words, each open operator, each surjective operator between Banach spaces is a quotient map up to topological isomorphism. And similarly, this map from X to Y is a co-isometry, if and only if the induced map is an isometric isomorphism. So co-isometries are also quotient maps, but now up to an isometric isomorphism. So both theorem 1 and theorem 2, in some sense, they establish duality between inclusions and surjections. But theorem 1 is about topological inclusions and topological surjections. And theorem 2 is about isometric inclusions and isometric surjections. Okay, before we formulate the next result, let's recall the pure algebraic definition of a co-kernel for a linear operator. Suppose that X and Y are vector spaces, just vector spaces. They are not equipped with any norms. And T is a linear operator from X to Y. And we define the co-kernel of T to be the quotient of Y modulo the image of T. Well, this is just the usual linear algebraic definition of a co-kernel for linear operators. For those of you who are familiar with the language of categories, I'd like to note that, in fact, there is a more general category theoretic definition of a co-kernel, which makes sense for any category with zero object. And so if we look at this definition, this is precisely the definition of a co-kernel in the category of vector spaces. If we consider, for example, the category of Banach spaces and bounded linear operators, then the category theoretic co-kernel will be different from this one. It will be the quotient modulo the closure of the image. Well, however, there will be no confusion here because we will actually apply this notion, the notion of a co-kernel, only in the case of operators with closed image, with a closed image. So in this case, the category of theoretic co-kernel in the category of Banach spaces, and this definition are in fact identical. Okay, now we have the following result, theorem 3. Theorem 3. Again, suppose that X and Y are Banach spaces, and T is a bounded linear operator from X to Y. Then the following conditions are equivalent. Condition 1, the image of T is closed in Y. Condition 2, the image of the dual operator, T star, is closed in X star. Condition 3, the image of T equals the pre-annihilator of the kernel of T star. And finally, condition 4, the image of T star equals the annihilator of the kernel of T. So these 4 conditions are equivalent. And moreover, if these conditions are satisfied, if they are satisfied, then there exist isometric isomorphisms. Isometric isomorphisms between the kernel of the dual operator, kernel of T star, and the dual of the co-kernel of T. And similarly, the co-kernel of T star is isometrically isomorphic to the dual of the kernel of T. And this is the so-called closed image theorem. The closed image theorem. So basically, this theorem states that the image of T is closed, even only if the image of T star is closed, and gives also some more information about operators with closed images. Okay, let's now try to prove this result. First of all, let's observe the trivial equivalence. It's almost trivial that that 1 and 3 are equivalent. This is clear because we already know from the previous lecture that for an arbitrary linear operator between norm spaces, the closure of the image of T, equals the pre-annihilator of the kernel of T star. And this equality holds for each bounded linear operator T. And of course, this formula implies that the image of T is closed if and only if the image of T equals the pre-annihilator of the kernel of T star. So conditions 1 and 3 are equivalent. By the way, it seems from at least when we look at this statement, it seems that 2 and 4 are related in the same way as 1 and 3. But this is not the case. In contrast to 1 and 3, the equivalence between 2 and 4 is not obvious at all. Because in general, let's recall that in general, we cannot claim that the closure of the image of T star equals the annihilator of the kernel of T. In other words, we cannot interchange T and T star here. In the general case, we know that the closure of the image of T star is contained in the annihilator of the kernel. But nevertheless, we will see soon that 2 and 4 are indeed equivalent. But first of all, let's show that 1 implies 4. 1 implies 4. So we assume that the image of T is closed. And we want to show that the image of T star equals the annihilator of the kernel of T. To prove this implication, we factorize T through the quotient module of the kernel. So we look at the following picture. This is T. This is the quotient module of the kernel. This is the quotient map. And this is the induced operator T0. And let's also draw the dual picture, X star, Y star, and the dual of the quotient. And here we have Q star, T star, and T0 star. Well, by assumption, T is the image of T is closed. So since the image of T0 is equal to the image of T, It's clear from the first diagram. This implies that the image of T0 is also closed. On the other hand, since we quotient out the kernel, we see that T0 is injective by construction. And we know that the open mapping theorem implies that an injective operator with closed image between Banach spaces is topologically injective. The open mapping theorem implies now that T0 is topologically injective. But then we know that in this case, T0 star is surjective. The dual operator T0 star is surjective. We now look at the second diagram. The second diagram is also commutative. And the surjectivity of T0 star implies that the image of T star, well, T star is a composition of T0 star and Q star. But T0 star is surjective, so the image of T star is equal to the image of Q star by the surjectivity of T0 star. But we know everything about the image of Q star. So in the previous lecture, we proved that if we take any closed vector subspace of a normed space, so in our situation, this is the kernel of T, but we can take any closed subspace and consider the quotient map, then the dual of the quotient map is an isometry onto the annihilator. And so the image of Q star is nothing but the annihilator of the kernel of T. This follows from the previous lecture. And that's it. This is exactly condition 4 of our theorem. So we proved that if T, the image of T is closed, then the image of T star is equal to the annihilator of the kernel of T. So 1 implies 4. Well, now it's clear that 4 implies 2. Of course, the annihilator of the kernel is always a closed vector subspace. The annihilator of any set is a closed vector subspace. So clearly 2 implies 4. Oh, sorry, 4 implies 2. So so this formula, the image of T equals the annihilator of the kernel, obviously implies that the image of T star is closed. And to complete the proof, we need to show that 2 implies 1. That is, if the image of T star is closed, then the image of T is closed. Again, we factorize T in a suitable way, but now we factorize T through the closure of its image. In other words, we look at the following picture. This is the closure of the image of T. This is T. This is the inclusion map, J. J is the inclusion map. And here we have the induced map, T0, which acts by the same rule as T does. And we also consider the dual picture. This is X star, Y star. Now take the dual of the closure of the image. And here we have T star, J star, and T0 star. Okay, now what can we say about these pictures, these vector pictures? Well, first of all, what is J star? J is the inclusion map. And by the definition of the dual map, we easily see that J star is the restriction map. We have already observed this at the previous lecture. J star is the restriction map. so it is surjective by the Hahn-Banach theorem. And if we now look at the second diagram, which is commutative, we conclude that the image of T0 star equals the image of T star. By the commutativity of the second diagram and by the surjectivity of J star. But by assumption, the image of T star is closed. So the image of T0 star is closed. On the other hand, by construction, the image of T0 is dense. T0 has dense image just by construction. So T0 acts from X to the closure of the image of T. So T0 has dense image, and we know that the dual of a dense image operator is injective. This implies that T0 star is injective. And again, we see that T0 star is an injective operator with closed image. But again, the open mapping theorem implies that such an operator is topologically injective. By the open mapping theorem. But we already know that if the dual operator is topologically injective, then the operator itself, namely T0, is surjective. This follows from theorem 1. T0 is surjective. But the surjectivity of T0 means exactly that the image of T is closed. And this completes the proof of our implication. So we now see that all 4 properties, 1, 2, 3, and 4, are equivalent. But this is not the end of the story. We also have to show that if these conditions are satisfied, then we have two isometric isomorphisms, this one and this one. Okay, let's show that this is indeed the case. So we now suppose that conditions 1, 2, 3, and 4 are satisfied. And let's look, for example, at the dual of the core kernel of T. So the core kernel is the quotient module of the image. And let's recall now from the previous lecture that the dual of the quotient, modulo a closed vector subspace, is isometrically isomorphic to the annihilator. So this is isomorphic to the annihilator of the image of T. But we already know that the annihilator of the image of T, this is formula 3, is nothing but the, where is it? Oh, it's not here. Well, anyway, we know from the previous lecture that the annihilator of the image of T is nothing but the kernel of T star. This is true for any linear operator. And this gives us the first isometric isomorphism. So the dual of the core kernel of T is the kernel of T star. And similarly, if we take the dual of the kernel, again, we apply a theorem from the previous lecture, which states that the dual of a vector subspace is isomorphic, isometrically isomorphic to the quotient modulo of the annihilator. So this is isomorphic to X star modulo of the annihilator of the kernel of T. But now we apply formula 4. So we know that the annihilator of the kernel of T is nothing but the image of T star. So this is the quotient modulo of the image of T star. But this is nothing but the co-kernel of T star. And that's it. This completes the proof of theorem 3. Okay, that's it. Oh, by the way, it seems that I forgot to tell you some words about the proof of theorem 2. Let's look once again at the statement. So theorem 1 was proved at the end of the previous lecture. And the proof of theorem 2 is, actually, this is a nice exercise for you, because the proof of theorem 2 is almost identical to the proof of theorem 1. So just take the proof of theorem 1 and make some little, more or less obvious modifications to get the proof of theorem 2. Let me write this down explicitly. The proof of theorem 2 is an exercise and it is similar to the proof of theorem 1. Okay, so let's now look at a nice corollary of the closed image theorem. This corollary is sometimes called Johnson's lemma. Because it is essentially due to Barry Johnson. Suppose that we have 3 Banach spaces, X, Y, and Z. And 2 bounded linear operators. So T is a bounded linear operator from X to Y, and S is an operator from Y to Z. Then the following conditions are equivalent. Condition 1, so we can form following diagram, following sequence. This is T and this is S. So property 1 is that this sequence is exact. And the image of S is closed. And property 2 is dual to 1. We now consider the dual picture, Z star, Y star, and X star. And this is T star, and this is S star. So property 2 is that this sequence is exact, the dual sequence is exact. And the image of, this one should be S star, of course. And this one is T star. So I hope now it is correct. So this is the dual. The sequence is dual to 1, and property 2 is that the dual sequence is exact and the image of T star is closed. So in other words, this property, the property is that the sequence is exact and the image of the second arrow is closed. So this property is stable under taking the duals. And the other way around, if this property holds for the dual sequence, then the same property holds for the original sequence. This result is very useful in numerous homological applications of functional analysis. And the proof is an easy corollary from the closed image theorem. Let's show that 1 implies 2. First of all, we show that the dual sequence is exact. That is, the kernel of T star is equal to the image of S star. Well, first of all, the kernel of T star is the annihilator of the image of T. This is true for any bounded linear operator between Banach spaces. Now the first sequence is exact, so the image of T is nothing but the kernel of S. But by assumption, the image of S is closed. So the operator S satisfies conditions of the closed image theorem. And we know that for such operators, the annihilator of the kernel is exactly the image of the dual. Well, just a moment, I have to look at the time because just a moment. Okay, so we know that the annihilator of the kernel of S equals the image of T star, or image of S star, the image of S star. And that's it. So we see that the kernel of T star equals the image of S star, that is, the second sequence is exact. Also, we have to show that the image of T star is closed. And why is it so? Well, the image of T star is closed. It is indeed closed because the image of T is closed. And why is the image of T closed? The image of T is closed because the image of T is equal to the kernel of S by the exactness of the first sequence. And the kernel of any bounded linear operator is always closed because it is the pre-image of 0. And this completes the proof of the first implication. So 1 implies 2. And let's now show that 2 implies 1. Again, we have to show that the first sequence is exact. We take the kernel of S. And we want to show that the kernel of S is equal to the image of T. Well, the kernel of S is the pre-annihilator of the image of the dual operator. This is true for any bounded linear operator between normed spaces. But the second sequence is exact. So the image of S star is equal to the kernel of T star. And the pre-annihilator of the kernel of the dual operator is equal to the closure of the image of T. But since the image of T is assumed, since the image of T is closed because the image of T star is closed, we conclude that this is nothing but the image of T. So the image of T star is closed by assumption, and this implies that the image of T is closed. And we see that the first sequence is exact. So the kernel S is equal to the image of T. And finally, we have to show that the image of S is closed. And here we use the same argument. The image of S is closed because the image of a star is closed. And the image of a star is closed because it is equal to the kernel of T star by the exactness of the second sequence. And the kernel of any operator between normal spaces is closed. And that's it. And as a special case of Johnson's lemma, we get the following result, one more corollary. Suppose that we have a chain complex of Banach spaces. That's denoted by C. So Cn is the nth space, and Dn is the respective differential. So I claim that it is exact, even only if the dual complex is exact. So if we now have a chain complex of Banach spaces, so Cn is the nth space in this complex, and Dn is the respective differential, then we see that, well, obviously we can form the dual complex C star, which consists of dual spaces and dual operators. And this will be a co-chain complex, of course. So we see the chain complex of Banach spaces of well, let me write this down once again. The chain complex of Banach spaces is exact even only if the dual complex is exact. To prove this corollary, we simply apply the previous one. We simply apply Johnson's lemma to each part of C consisting of three consecutive terms, Cn minus 1, Cn, and Cn plus 1. And we see that we observe that Johnson's lemma indeed applies because if the original complex is exact, then all the differentials have closed images, because the image of each differential is equal to the kernel of the next differential. And so the conditions of Johnson's lemma are satisfied. We apply this lemma and we conclude that if the complex is exact, then the dual one is exact and the other way around. Okay, probably that's all I wanted to tell you about the general duality theory for Banach spaces. And now we are ready to introduce Fredholm operators. Well, the definition of a Fredholm operator is purely algebraic. Suppose we have two vector spaces, X and Y. Just vector spaces without any norm. And T is a linear operator from X to Y. And we give the following definition. We say that T is a Fredholm operator. If the kernel of T and the co-kernel of T are finite dimensional. So we see that the definition is purely algebraic. It makes sense for any linear operator between any pair of vector spaces. But of course, we will be mostly interested in the functional analytic side of this notion. And we adopt the following standard convention that if T is an operator between Banach spaces, we say that T is Fredholm if this condition is satisfied and if T is bounded. So if X and Y are Banach spaces, then we will also assume that the Fredholm operator is bounded. It is assumed to be bounded. Fredholm operators are named after Ivar Fredholm, a Swedish mathematician, who actually had no idea about linear operators and about vector spaces. In fact, Fredholm worked with the theory of integral equations. And his fundamental results on integral equations, which were obtained in 1903, were later translated by Ries into the language of linear operators. And the modern definition of a Fredholm operator was given by Dieudonné only in the 1940s. For each Fredholm operator, we can introduce a very important number, the so-called index. We define the index of a Fredholm operator T to be the difference between the dimension of the kernel and the dimension of the co-kernel. This is the index of T. And we will see soon that the index has many nice and useful algebraic and topological properties. Let's look at some examples of Fredholm operators. Example 1 is quite trivial. We observe that any isomorphism any vector space isomorphism is a Fredholm operator. For obvious reasons, the kernel is trivial and the co-kernel is trivial. And so the index is equal to 0. Example 2. Suppose that we have a projection on a vector space X. What does that mean? This means that we have a direct sum decomposition. X is the direct sum of two subspaces, X0 and X1. And P acts by the following formula. It takes little X0 plus little X1, where the summands belong to the respective subspaces, to X1. This means that P is a projection on X, a projection onto X1 along X0. And suppose that the kernel is finite dimensional. Suppose that X0 is finite dimensional. Then let's observe that in this case, P is Fredholm. And the index is 0. Well, indeed, for any projection, we can easily see that the co-kernel is isomorphic to the kernel. So x1 is nothing but the image of P. So when we quotient out the image, we get something which is isomorphic to x0. So the kernel of a projection and the co-kernel of it are isomorphic. And so if x0 is finite dimensional, we conclude that P is Fredholm and that the index is 0. Example 3. Suppose that we have two finite dimensional vector spaces. Then, of course, any linear operator T from X to Y is Fredholm. And this is clear. And also I claim that the index of T is equal to the dimension of X minus the dimension of Y. So actually in this case, in the finite dimensional case, the index of T doesn't depend on T. It depends only on the dimensions of the spaces X and Y. And indeed, this is very easy. So by definition, the index of T is the dimension of the kernel minus the dimension of the co-kernel. And the co-kernel is the quotient of Y modulo the image. And we know that in the finite dimensional case, the dimension of the quotient is equal to the dimension of Y minus the dimension of the image. And so we see that this can be written as the dimension of the kernel plus the dimension of the image minus the dimension of Y. But we probably know from elementary linear algebra that the sum, the dimension of the kernel plus the dimension of the image, is nothing but the dimension of X. So we get the desired formula. And in particular, we see that if T acts from X to itself, where X is a finite dimensional vector space, then the index of T is 0. So we see that in the finite dimensional case, the notion of the index is not very useful because of this observation. But we are mostly interested in the infinite dimensional case. And in the infinite dimensional case, we can construct many non-trivial examples of Fredholm operators. For example, let's look at shift operators. Example 4. Let X denote either the little LP space or the little C0 space. And let's consider the left shift and the right shift operators. TL is the left shift, and TR is the right shift. And it's easy to see that both of them are Fredholm. They are Fredholm. The index of the left shift is 1, and the index of the right shift is -1. Well, indeed, why is it so? Well, the left shift is surjective, so the kernel is trivial. But the kernel of the left shift is non-trivial, and it's more or less clear that the kernel of the left shift is one-dimensional. It consists of all sequences such that the first coordinate is arbitrary and all the remaining coordinates are 0. So this is exactly the kernel of the left shift, and it is one-dimensional. So the index of the left shift is 1. And if we look at the right shift, well, the right shift is injective, so the kernel is trivial. But the image of the right shift is a codimension 1 subspace. The image of the right shift is the space of those sequences such that the first coordinate is 0. So this is clearly a codimension 1 subspace, and so the co-kernel is one-dimensional. And therefore, the index of the right shift is -1. Okay, so these are the simplest examples of Fredholm operators. Some more examples will be contained in our next exercise sheet. And some more advanced examples will be discussed at the lectures. And by the way, probably the most important class of Fredholm operators consists of so-called elliptic differential operators on manifolds. And the most important result in their theory is the famous Atiyah-Singer formula, which expresses the index of an elliptic operator in purely topological terms. But unfortunately, even an elementary introduction to elliptic operators requires a separate course. And that's the reason I'll tell you nothing about them. On the other hand, we'll discuss soon another interesting class of Fredholm operators, the so-called Toeplitz operators on the unit circle, and we get a useful index formula for Toeplitz operators, which also has an interesting topological flavor. Okay, let's now prove some general results about Fredholm operators and about the index. One of the most interesting and important algebraic properties of the index is the additivity of the index. So we have the following theorem. Suppose we have 3 vector spaces, x, y, and z. And 2 linear operators, say t from x to y, and s from y to z. Then we have the following results. First of all, if we consider T as and their composition, and if any 2 of these 3 operators are Fredholm, if any 2 of the operators S, T, and ST are Fredholm, then so is the third one. So in particular, we see that the composition of 2 Fredholm operators is Fredholm. Second, if condition 1 is satisfied, so if they are Fredholm, then the following formula holds: the index of ST is equal to the index of S plus the index of T. This is the additivity of the index. And property 3, suppose that the composition ST is Fredholm. Oops. Okay, so part 3 states that if the composition of our operators S and T, if ST is Fredholm, then in general we cannot claim, of course, that S and T are Fredholm, but at least we can claim that the kernel of T is finite dimensional. The kernel of T and the co-kernel of S are finite dimensional. Well, probably the most important part of this theorem is that the composition of two Fredholm operators is also a Fredholm operator, and that this formula holds. A remarkable property of this theorem is that this theorem has no canonical proof. There are several different proofs, and probably none of them is the optimal one. I'll tell you the proof which I learned from Mikhail Alexandrovich Shubin, and which has some nice homological flavor. The proof depends on two elementary algebraic lemmas. Lemma 1. Suppose that we have an exact sequence of finite dimensional vector spaces of the following form. A finite exact sequence of finite dimensional vector spaces. I claim that in this case, the following alternating sum of their dimensions is equal to 0. The proof is an elementary exercise in linear algebra. just use induction on n. Then lemma 2 is a very well-known result. This is a special case of the so-called snake lemma. Well, suppose we have the following commutative diagram for the following form. So we have two rows in the diagram. And three columns, alpha, beta, and gamma. And suppose that this is a commutative diagram of vector spaces. With exact rows. In fact, vector spaces can be replaced here by modules over any ring or by objects in any abelian category. I claim that in this case, there exists a 6-term exact sequence. An exact sequence of the following form. The kernel of alpha, the kernel of beta, the kernel of gamma, and then we have the co-kernel of alpha, the co-kernel of beta, the co-kernel gamma, and 0. This result is fairly standard, so I'll not give you any proof. I'll just explain why it is so called. Why is it the snake lemma? If we look at the resulting exact sequence, it's more or less clear where, for example, the first arrow comes from. The first arrow between the kernel of alpha and the kernel of beta is just the map which is induced by the first arrow in this diagram. So this is the map between the kernels. And similarly, the second arrow between the kernel of beta and the kernel of gamma is induced by the arrow from x2 to x3. And similarly, the maps between the co-kernels, I mean this one and this one, are induced respectively by the maps from y1 to y2 and from y2 to y3. So what is not entirely obvious is this arrow. So what is the arrow from the kernel of gamma to the co-kernel of alpha? This arrow can be visualized as a snake from here to here. And this is the reason why the snake lemma is so called. And the proof is the standard diagram chasing. So you just take an element in the respective space, suppose that this element sits in the kernel, and try to show that it comes from the image of the previous arrow, just by looking through the diagram. This is more or less standard. Okay, let's now apply these two results to the proof of our theorem about the Fredholm index. So we consider the following diagram. Well, first of all, we have X, this is the first space in our diagram. X plus Y and Y. So the first map from X to X plus Y is, well, T, well, maybe, oh, sorry, not T. We can denote this map as a column 1 and T. And it's more or less clear from the notation what it means. So X goes to X plus Y, 1 is the identity map of X. So each element of little x in X goes to the pair X and T of X. And we denote this respective operator as a column 1 and T. A second arrow is a row, and we can write it as minus T and 1. Again, the notation is self-explanatory. So this operator takes each pair, little x and little y, in this direct sum, to minus T of X plus Y. And here we have 0. This is the first row of our diagram. And the second row looks as follows. I have Y, Z plus Y, and Z. So this is S and 1, the identity map. And this is the row minus 1 and S. And this is the second row. And the columns are as follows. This is S, this is T, and this is S t plus 1. So this operator acts as st on x, and it takes x to z, and it is the identity map on the second summand. Now it's elementary to show that the diagram is commutative, and that the rows are exact. This is a trivial exercise for you. And now we apply lemma 2, the snake lemma. Lemma 2 implies that we have the following exact sequence. And 0, the kernel of S. Then we have the kernel of st plus 1. And then we have the kernel of t. And then we have the co-kernels, the co-kernel of S, and the co-kernel of st plus 1, and the co-kernel of t, and 0. Okay, so we now look at the sequence, and we observe that the kernel of st is obviously isomorphic to the kernel of st plus 1 is obviously isomorphic to the kernel of st. And similarly, the co-kernel of st plus 1 is isomorphic to the co-kernel of st. And this exact sequence really implies properties statements 1 and 3 in our theorem. So let's recall that property 1 states that if any two of the operators st and st are Fredholm, then so is the third one. And this is immediate from this exact sequence because, well, if we have an exact sequence of vector spaces, and if we take a space in the sequence such that it is in the middle between two finite dimensional spaces, then the space itself is finite dimensional by the exactness. So if, for example, we assume that if S and T are Fredholm, then this is finite dimensional, this is finite dimensional, but then this implies that the kernel of ST is also finite dimensional. And similarly for the co-kernels. So ST is Fredholm. And the sign argument shows that, for example, if S and ST are Fredholm, then T is Fredholm. And property 3 states that if ST is Fredholm, if this one is Fredholm, then the kernel of S is finite dimensional and the co-kernel of T is finite dimensional. But this also follows from the same exact sequence. So now to complete the proof, we have to prove the additivity of the index. And to prove the additivity of the index, we apply lemma 1. Lemma 1 states that the alternating sum of the dimensions in the sequence is 0. Well, let's form the alternating sum. So the kernel of S goes with the plus sign. The second summand goes with the minus sign. Plus, minus, plus, and minus. And then we form the alternating sum. We see that this summand together with this one gives us the index of S. Now, this summand together with this one gives us minus the index of ST.
Извините, у нас меньше минуты осталось.
Да, все, практически все. And finally, these two summands, I mean, this one and this one, they give us the index of T. And this completes the proof. Okay, so that's all for today. Thank you. At the next lecture, we continue our study of Fractal operators and prove some more interesting properties of the index. Thank you.
Thank you.
Спасибо.
Bye.